What I'm going to do now is I'm going to apply the particle in a box model to the molecule butadiene. Butadiene is a molecule that has two double bonds, but you might have heard of the idea of conjugation in organic chemistry. And so the bond in the middle is a little bit shorter than a typical double bond, and the double bonds are a little longer than a typical double bond. It turns out that the bond is delocalized through the molecule. We'll talk about that more a little bit later, but for right now, we're just going to assume that we can model this as a molecule, as a box, which has a total length, which is the length of the molecule. In this case, 130 picometers plus 150 picometers plus 130 picometers. This molecule has 4 pi electrons, and we're going to fill those in to these particle in a box wave functions in the same way that we would fill them into molecular orbitals. And so I'll write them in like this. Okay. Now, our question is, how can we observe this? Well, one of the ways we can observe this is through the visible transition, in this case, will turn out to be ultraviolet transitions of butadiene. If I take one of those electrons and I move it to the next level, and this is how I have transitions. I move an electron from a level that's occupied to a level that's empty. And now what do I see? I see a delta E for the electron is going to be equal to the energy of the third level minus the energy of the second level. The third level where it went to, the second level where it came from, which is going to be equal to 9E1. You see that the energy is equal to m squared h squared over 8ma squared. So the energy of a given level is n squared times E1. I'm using a little shorthand. So E3 is 9E1 minus E2, which is 4E1, equal to 5E1. That is my energy of my photon. If I take, or equal to 5h squared over 8ma squared. Now, if I take this and I put in my values that A is equal to 410 picometers, that M is equal to M sub E, which is 9.31, if I remember right, let's see, 9.1 times 10 to the minus 31st kilograms. I put in my value for H. What I'm going to obtain is that delta E is equal to 1.79 times 10 to the minus 19th joules. I will leave it as an exercise to you to figure out that E is equal to hc over lambda, and that solving for lambda gives me a wavelength of 111 nanometers. That's a little bit higher energy than it actually is, but still, this isn't a bad approach, and does also explain to us a little bit about the bonding in butadiene. If I look, one last piece I want to add, I have electrons in these two levels, psi squared, psi 1 squared, psi 2 squared. Roughly speaking, what this tells me is that the ground state is bonding through all of the molecule. If this is, let's suppose this is C1, C2, C3, C4, that the second wave function has no electron density between C2 and C3, but when we add these up, they don't quite cancel each other out. And we get some bonding character between these two carbons. And that's exactly what we see in the molecule. So this model actually does pretty well for us.